Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel. And in today's video, we are going to discuss how to derivate an implicit function. So, what exactly an implicit function is? If I just try to mention here a bivariate function, for example, if you are having a function like this, just for instance, if you are having a function like this, it is a bivariate or an equation involving two variables. That's why I'm saying it, bivariate function. So from in this function, it is hard for us, or it's almost impossible to separate or to form an equation keeping y a subject, or to modify this equation giving it a form like this, keeping y the subject and trying to explain it as a function of f, so a function of x. So once in such types of equation in which it is difficult for us, or it is impossible for us to separate this one variable from the other variable and trying to explain it with respect to this form, so such kind of functions are called the implicit function, and we just call this equation as the functional equation, as the functional equation. We just represent it with our capital F, xy equals to 0, of function f. All right, so this is it. So I hope you have understood the concept of what exactly an implicit function is, and those equations, bivariate equations, in which it is easy for us or possible for us to separate the variables and try to express it in this form, such kind of functions are called the explicit functions. Okay, so now the question arises that once it's not possible for us to separate y from this equation and try to express in this form, it's not possible, but at least it is possible for us to find out its derivative, means to find out the derivative of your y. Okay, though we are not able to transform or to modify or to express this equation in this form, but at least we can find out the derivative of this y. So now in this video, we are going to learn how to derivate such kind of functional equations of the function f, and let us try to figure it out and try to understand by a few examples here. So here you go, the very first example. Okay, I've just picked up the very same equation right over here, and let us try to solve it out and try to find out the derivative of this y with respect to our x. For that purpose, I just call this equation, I just give it a name at equation 1 here. And I'm going to now differentiate this entire equation, a functional equation with respect to x. So now we are going to differentiate it gently. Equal to, and you know the derivative of your 0 is 0, it's a constant number, so no need to write anything over here. So you just go on at your, keep yourself active at the left side. Okay, so now we are going to apply this differential operator individually in all these three terms. We just have to follow the intrinsic rules of your derivative exactly here. 3 and a, these are the constant values, so you just write it down outside your differential operator, and over here you simply write your xy, and it's 0. So now over here you are well aware you are going to use the formula of your x power n, which is nothing but this, that we have proven this formula in my previous video that deals with the ab initio method, how to solve the how to find out the derivative through first principle. Over there we have derived this thing. You can see it if you want to, the link is in the description box. So this is it. Now it is, suppose this is n, so it is 3x 3 minus 1. And over here you're going to use the same formula, but as you can see that the variable over here is not the variable which is mentioned along with the differential operator, so you have to apply a chain rule. So it is going to be something like this. Okay, you have just applied a chain rule on the base of this function. All right, and at this side you're going to use here the formula of your u into v. If you're having two functions in product form, and how you apply what formula you use here if you're using two functions, for example, u and v. Okay, then you just perform this formula. I'm just writing this in reference for your convenience. Okay, so we are using this formula right over here. Okay, so let me put down a parentheses, and it is x dy by dx plus y dx upon dx, which is nothing but 1. Okay, and it is 0. So now what is now left here is 3x squared plus 3y squared dy by dx plus 3ax dy by dx, all right, plus 3ay, and this is your ones. Okay, so no need to mention this thing now in this step. It's simply 3ay equals to 0. Now what we do now here, we are just going to move those terms which are without this dy by dx over here at the right side, and at this side just dy by dx terms will be left. We are going to keep them right over here. Okay, so this is going to be, that's how it looks like. All right, now over here I can take out my dy by dx common. Okay, and 3 is also coming out common, so it's going to be like this, dy by dx. Okay, my d is too horrible, and over here the negative 3 is coming common, so inside will be ay plus x squared. That's what is left here. Now I can cancel this 3 and 3, and this is a multiplicative term which is getting multiplied with this, so when it moves on the other side it goes in the denominator. You are quite acquainted with this basic algebraic rule, so it is. Let me organize these terms with respect to the powers, and this thing will go downwards, and it looks like this. So this is it. So you see, and it simply equals to, right? It simply equals to. So that's how you just try you just evaluate or you just figure out your dy by dx, the derivative of such functional equation through which it is impossible for us to form a function keeping y the subject, and forming a function with respect to x keeping y a subject. So but at least we can calculate its derivative, and we just did that. So let's move ahead to one more example, and then it'll be quite sufficient enough for us to get this entire topic. So let's move on to the next example. Okay, here you go, another example. And this is a functional equation of an implicit function. Okay, this is an implicit function. You are unable to separate your y and your x, forming a certain function of this form. So this is an implicit this is a functional equation of this function f. Okay, so we have to find out its derivative of this y. So what you do, you just call it equation 1 for your convenience, and you just differentiate both sides with respect to your x. All right, my objective is to find my y dash, or my dy by dx. There are several representations, so that's what I have to find out. So I'm going to differentiate both sides with respect to my x. All right, So differentiating both sides of our equation 1 with respect to x. Okay, begin. All right, so now you are differentiating very carefully. And that's what we are doing here. Okay, so over here you can see you're having two functions. One is exponential, another one is logarithmic. So you are going to use this formula of two functions that we have just mentioned in the previous example. No need to give the reference here. So there's no need to give the reference here of how to find out the derivative of the product of two functions. So let us do it directly. And it is, for example, this is your u and this is your v. So it is u derivative of your v, just like that, plus v derivative of your u. All right, and this sine inverse y, the derivative of sine inverse y with respect to x, that's what we have to do. So it is is 1 minus y square, and you're going to use here your chain rule because it is not simply x. It is not simply x. This is a variable other than x. So you just take out the chain rule of this angle value, and it looks like this because you know the formula. Let me mention here the reference because I think it's mandatory. So if you just have a formula like this, and it is under root 1 minus x squared. This is the formula of your sine inverse x, the derivative of sine inverse x. And once when you just take out the chain rule on this value, it is dx upon dx and simply 1. That's why it is not mentioned in the formula. So this is the logic which is going on behind. So we just use here this formula over here. Okay, now let us do it further. And this notation tells that still a step, one more step is going to be taken now. Now it is the derivative of your log of any value it's the reciprocal. It is the reciprocal, and this is still y. So you just perform here chain rule like this. And then you move on over here. We come over here. The derivative of exponential of any power, having any power, is exponential itself. And then you apply chain rule on this power. It is x already. So just for understanding, if I apply chain rule here, you're having 1. So no need to mention chain rule in such cases. But I'm just telling just for exhaustive representation. So, and it is going to be copied as it is. All right, so now what else? It is e power x upon y dy by dx plus e raised to the power x ln y is equal to 1 upon under root 1 minus y square dy by dx. Now our objective, the next objective, is to collect or to shift all the terms involving dy by dx on one side. So how about if I just shift this side over here and this over here? Also, you can shift this side over here and keep this thing as it is at its place. So we just do it, and it is this. Okay, so it is 1 upon under root 1 minus y square dy by dx at its place, and you just simply move this thing over here. It becomes negative. All right, so it is dy by dx. All right, so now you just take it out common, and then we try to further solve this thing by using the basic arithmetic rules. Okay, so it is. Though it is something algebraic, but the rules in algebra, the basic rules in algebra are basically derived from that of arithmetic. That's why I use the term arithmetic. Okay, so it is. Let me take out the LCM now here. So I hope big learners are very much acquainted with the preliminaries, so no need to repeat this thing, I hope. So I'm directly using the LCM. The LCM is going to be here, y minus this. Okay, this is my LCM. Now keep this thing as it is at its place and just shift this thing on the other side, so this thing will move in the numerator at the left hand side, and this thing entirely, this thing, the numerator at the of the right hand side, will move in the denominator side at the left hand side. Okay, so you just try to figure it out. For my convenience, I can simply write this thing at the left side and this thing entirely at the right side without any changes in the sign. So this is a simultaneous shifting, what we say. So this will help in understanding the swapping, because dy by dx conventionally it is written at the left hand side. All right. So that's what I've done here. Now you just shift this thing over here and this thing in the denominator, and you are done. And it's all finished. Okay, so this is your beautiful derivative of your function y is equals to f of x, whose functional equation was provided to us, and it was impossible for us to separate our y from our x and try to express it in terms of y is equals to f of x. So this was an implicit function. So with the provision of its functional equation, we just find ourselves able to derivate that functional equation and obtain the derivative of our y. Okay, so that's all for today, and inshallah in the next video we'll try to come up with some more fruitful topics regarding to the differentiation and other topics on the calculus and so on. So if you find this video helpful, I humbly request you to subscribe my channel, hit on the like, hit on the bell icon, and share this video as much as you can as usual, and try to put down your feedback in the comment box, and I'll be highly appreciated like that. So okay then, take good care of yourself, study well, score good, develop high, live well, be happy. Allah Hafiz.